Hi viewers, welcome to all. Here we are discussing about a project low power high precision floating point divider with a bidirectional linear approximation. Here the floating point division is a critical operations in many applications such as image processing, signal processing, scientific computing and neural network accelerators, where accuracy and speed are essential but hardware resources and power consumptions become a major concern. Here the conventional floating point divider achieves a high precision but suffers from large area, high delay and increased power usages, making them less suitable for recent applications. Here there are several existing approaches such as iterative algorithms, reciprocal based methods and logarithmic techniques have been explored to reduce the complexity, but this still involve multipliers and large lookup tables and deeper pipeline stages that add to hardware cost. To address this limitation, this proposed an approximate floating point divider architecture that combines the truncations and small LUT based coefficient storages and carries save adder block to simplify the designs and reduce computations overhead. Further, this improvement is achieved by developing an optimized XOR mux based full adders and subtractions which significantly minimize the area and power consumption. So when compared to this conventional arithmetic unit, the novelty of this design lies in the replacing complex multiplications with a lightweight logic structures when maintaining acceptable accuracy, thus achieving an effective trade-off between a performance and resource utilization. The proposed divider is described and verified in Verilog HDL and synthesized and evaluated in terms of area, power and delay metrics. Now we can verify the paper. So this paper is fully designed for the floating point divider with a bidirectional linear approximation. So instead of the existing architecture and traditional architecture of the floating point division method, here we introduced a truncated and LUT based floating point division method. Here the figure 1, it will be showing the structure of the proposed mantissa divider. So this is a traditional architecture, but in this paper they will be used for the truncated method. So here this is a proposed architecture, it will be mentioned in figure 1. So the floating point representation for the real number x in a single precision format. So it's look like as the same as a floating point multiplier, but here it will be doing a division operation. So here initially we start with the input, it will be referred with a sign bit, exponent and mantissa. The sign bit always it will be doing a XOR operation, and exponent always doing with a addition and bias based subtractions. It's also same for the floating multiplication, but here only thing is the mantissa, it's given a priority for the division. So this mantissa it will be come with a truncated part and also for LUT based reduction technique. So why we choose this LUT means, so this LUT, it will be reduce the number of multipliers and reduce the number of partial product based reductions and number of multipliers and subtractors and iterative loop compared to the other existing traditional designs. So here the mantissa divider, they will given a separate architecture for this division part. So here this is a division architecture. So here we need to give mx and my is a mantissa division operation, that is a 8-bit. So once we truncate it, it will come output at 5-bit size. So this 5-bit size we need to give 2-bit for LUT and 3-bit for multiplication operation. So in this multiplication operations, it's required a value, b value and c value. So these values we taken from the LUT. So depends upon the h size and the k size, the LUT it will be decided. So the LUT architectures also they will be given in the paper. So it's called as a coefficients of the divider in the case of nx equal to 2 and ns equal to 4, some values they will be given. So they will be mentioned a, b, c and d. So here the k value and h value, so we choose this architectures. So k value equal to 3 and h value equal to 2. So we designed f P D2 D4 cross 18 cross 18, 17 design architectures, and we prove the performance with the proposed design. So for the proposed designs, we choose a XOR mux based addition operations and XOR mux based subtractions operations. It will be reduce the number of logic gates in the additions and subtraction operations of this division part. So here the conventional designs, it will be occupied 5 logic gates in the additions and subtraction operation, but it will be taken only 2 logic gates and 1 multiplexes in the proposed design. So for that reasons, it will be come with a simple compared based proposed architectures. Okay, so here the figure 5, it will be showing LUT, right? So this LUT A, B, C, we need to give here the CSAB architectures, and we need to multiply it. So here this one is a 4x4 multiplier. After that, we'll take it as a product output. Okay, so this product output only we used in the top of the mantissa division. This architectures we developed in 2 different methods. One is for existing, another one is for proposed. Okay, so here we separately initiated this work for divider also. Initially we developed this divider architectures, and then we developed the floating point approximate divider architectures. Okay, so here the existing architectures, it will be designed using for conventional adders and subtractors, and the proposed architectures, it will be used for XOR mux based adders and subtractor. Okay, so this XOR mux based additions, it will be copied from this paper. Okay, so here the figure 6 it will be showing, but XOR mux based subtractors we created novelty architecture. Okay, so in this design, the first part is a division operation. Here this is a divider architecture code. It will be developed in Verilog HDL, and here we simplified it in modelism. Okay, so here you can verify the x input, y input, and approximate quotients value and exact quotients value here. Okay, so here you can check the value. Okay, so if we check with any value, it will be presents the exact, it will become with the accurate output, and the approximate quotient, it will become with the approximate output here. Okay, so here exact value, so we can possible to check this value in a calculator. Okay, so now I'll use this cursor, I'll place this in 2560 nanoseconds. Okay, so now it's showing this value, right? 4422784 divided by 14840. Okay, so it will become with a 298, it's accurate, that is the exact value, and 198 is the approximate value. Okay, so here this divisions we can run at a long time. Okay, so and we can check the analog pattern. Okay, so here you can verify it. This is the exact division output, and this is the approximate division output. Okay, so the approximate division output always it will be come with more accurate. Okay, and it will become with a less number of errors. Okay, and we analyze the error term calculations for this designs. Here we analyze the MED, NMED, MRED, and error rate. Okay, and we calculated this for 100%, and it will be put in the comparisons document. Okay, and we design a floating point multiplier architectures with the same Verilog HDL code. Okay, so this is a Verilog HDL code for floating point division operations. It will be divided using for 32-bit architecture, and this architectures it will be simulated in modelism. Okay, so here you can verify it, the floating point divisions of exact output and approximate output. Okay, and this is all the input. Okay, so exponent x and exponent y, mantissa x and mantissa y, and sin x and sin y. Okay, so here also we can check the exact value and approximate value in your graph basics. Okay, so here you can check the pattern. Okay, so exact and approximate value. Okay, then we synthesize this code in Xilinx Vertex 5 FPGA. Okay, so here this is a division code. Okay, for existing systems, and this one is a proposed design. Okay, and this one is for floating point division operations of existing code. It will be take 129 as a LUT, but in the proposed it will be occupied only 69 LUT. Okay, and slice register is equal to 14, and occupied size is equal to 42, and IOB equal to 62. Okay, so here we can verify the RTL schematic here. Okay, so this is the RTL schematic for this floating point division method. Okay, so here the x input and y input it will be given. Okay, so here we have 3 models. One is for XOR operation for sign configuration, and exponent for additions. Okay, additions, and mantissa. So mantissa it will be come with the coefficients LUTs and CSAB and truncated LSB part. Okay, so this CSAB having a multipliers. Okay, so the 2 multipliers we are used, and subtractions part and adder architecture. Okay, so this subtraction part, it will be developed using for XOR multiplexer based full subtractor. Okay, and this comparisons we compared it here. Okay, so this is a divider comparator, floating point with a divider. They using XOR mux comparisons, and this is a comparisons for a mantissa divider. Okay, so mantissa divider based single bit architecture. So here the mantissa divider only occupied 82 LUT, but in the floating point divider it will be occupied 129. Okay, so here 44 means it will be done with 62 in the XOR mux architecture. Okay, and we written abstract document for this project. This is a title and base paper abstract, improvement of the project, proposed title, proposed abstract. Okay, and related notes for this project. Okay, so existing, proposed, everything we are given, and finally we come up with the literature survey and references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.